Greetings, class. It's good to be back alive, but if you didn't catch up with the fact that I had a gallbladder removed, in the process I've lost 4 kilograms, so I'm a little lighter, but although I don't look much different, and a lot weaker. But I just wanted to very quickly go through and highlight a few key points from this particular PowerPoint. I know that most of you have already looked through it, but if you can just follow through, I will limit myself to about 10-15 minutes. So you're all familiar with the 3 states of matter that occur on Earth. And the particular thing that we want to emphasize here is the difference between intermolecular bonding and intramolecular bonding. It's like the internet and the intranet. Within the school we have an intranet, which is with internal, whereas between the school and outside there's the internet. So the intramolecular bonding is what we focused upon in the last unit, and this one we're really focusing upon forces between molecules. So this particular screen, if you want to stop and maybe take a few extra notes, that will be a good idea, but and then just restart the video. But we've already covered ionic, covalent and metallic. We'll cover a little more on that later, but the most important thing are these forces between molecules. So what happens is that you need to really learn about what APs calls London dispersion forces, which other people call van der Waals forces, and some people call van der Waals forces to cover all of these forces. Then you've got dipole to dipole interactions and hydrogen bonding. So that's what we're going to really draw out of this particular chapter. Those are key ideas. So the idea of London dispersion forces are instantaneous dipoles between non-polar molecules. Let me repeat that. Instantaneous dipoles between non-polar molecules. Then you have molecules which have a permanent dipole, which you're very familiar with, but the idea that that they have to have, if you remember, a polar molecule has to have polar bonds and it has to be asymmetrical. And then you've got these 3 types of molecules which have hydrogen bonding. Those where a hydrogen atom is attached to a fluorine, an oxygen, or a nitrogen. Sorry about that. My brain isn't woken back up again. So polar molecules have permanent dipole to dipole attractions caused by the attractions of slightly polar molecules. So here's what that looks like. Okay, they are permanent attractions between positive and negative ends of the molecules. Hydrogen bonding only occurs between where hydrogen is directly attached to oxygen, nitrogen, and fluorine. And this is because of the lone pair on the oxygen, nitrogen, and fluorine, which is attached to the hydrogen from the other molecule. So here's an example of water, which does hydrogen bonding. Okay, it's the best example of hydrogen bonding in terms of the importance it is to life as we know it. Without hydrogen bonding in the water molecule, we would not have life on Earth as we know it, and that is why scientists are constantly searching for water on other planets. So you can see the effect. If you start at H2S, as the core molecule gets heavier to go to selenium and tellurium, yes, the molecular forces increase just due to normal dipole London dispersion forces. But you can see this huge jump in boiling point from below 0, about -50, up to 100 degrees in the case of water. In the case of fluorine, again, HCl, HBr, HI, they gradually increase, but then this huge jump up to hydrogen fluoride. Same with ammonia. PH3, ASH3, SPH3, slowly increasing, but a huge jump from phosphorus up to nitrogen. So those 3 molecules, oxygen, fluorine, and nitrogen, have this special type of bonding, which we call hydrogen bonding. So notice it doesn't happen in carbon. Now, the next one that's a little hard to get a hold of is these London forces. Now, every single molecule and individual gas are attracted by these. And that's one of the things that whenever you answer an AP question on this, you really need to include London forces. Always list London forces. Then you can list the second force, but always list London forces. And these are rapid, random movements of the electrons can make one end of a molecule slightly positive, the other end slightly negative, instantaneously. Now this gets larger with more mass because there's more electrons. And so what happens is here's two atoms, they're bonded, but then the electrons all move down to one end, and that then induces an attraction in a neighboring molecule. So you can see the very bottom one, molecule A has a positive end, which induces a temporary dipole in molecule B, and therefore there's an attraction. So that's all there is about those sort of forces. I'll run another video on the liquid state. Thank you for listening, and do go back though. I'm just going to flick out of that to when you go into Power School Learning, what you'll see is under Unit 7, you can see the two POGIL worksheets that I set for today. Please go in and answer those. They're on alloys and solids. But also you'll see a number of AP questions. And one of the things that you can see, if I get to it, no, it doesn't want to let me in. Anyway, I'll just relaunch it. I've got my cameras on the road, so I'll relaunch it. You can see with these AP questions, yes, you've got the first part here is to do with the actual equation and some mass calculations. Second part draws in Kp. It's only the third part which really draws in this whole idea of the forces. And so it's identify all the types of forces. This is very common with AP questions, that this particular topic is going to be part of much bigger questions. So I have shared 5 questions with you. Don't attempt the electrochemistry part. So if it's got an electrochemistry part to the question, don't worry about it. But you should be able to answer all the other parts. And I'm going to choose one of these questions at random for a quiz next week. Okay, have a good weekend. Bye.